Welcome to Chapter 4. In this chapter, we'll be looking at graphing as well as optimization. In this first section, we're going to look at first derivatives and their graphs, and there's a lot of applications to business that you'll find in this chapter, so we look forward to learning a lot of new things. Okay, we've talked before about the first derivative is associated with the slope of the graph of a particular function at a point. So that is an important concept that we're going to be working with, and that's going to let us be able to find maximums and minimums of different things, and absolute maximums and minimums, and maximum revenue, minimum cost, things of that nature. We'll be able to do with this concept here. We'll be using sign charts, which we've talked a little bit about before, but that will kind of be primarily the way that we do this. And so we're going to go ahead and take a look at some of this. Okay, so with this one, you've got the function f of x equals x to the third minus 3x. If we look at the derivative of this, the derivative, we're going to bring the 3 down in front, so 3x squared minus the derivative of 3x would be 3. So if I look at factoring this, which a lot of times it is going to be helpful to factor it in order to do a sign chart, we would take the 3 out as a GCF, and so that's going to leave me with 3 times x squared minus 1. And then we're going to have the difference of squares here, so that's going to be 3 times x minus 1 and x plus 1. So what happens is we're actually going to get our critical numbers from these factors here, and that's going to be used when we do our sign chart. Okay, so our sign chart, we're going to break down into the -1 and the +1 because our derivative actually changes signs at, or could potentially change signs at these critical numbers here. So everything within this is going to behave the same way. Every number within this interval is going to behave the same way once it's plugged into our derivative. So any number I pick between -1 and 1, if I plug into the derivative, is going to give me a negative number. Any number that I plug in that's more than 1, and when I plug it into the derivative, is going to give me a positive number. And then any number that I plug in less than -1 is also going to give me a positive number. What that means for us in terms of the graph and in terms of any quantity that we're trying to talk about is if we have a positive first derivative, that means that our function is increasing. If we have a negative first derivative, that means it's decreasing. And then if we have a positive first derivative again, it means it's increasing. And that's important because we want to be able to find out, for instance, when is our revenue increasing, when is our cost decreasing, things of that nature. So it is an important concept to learn. And then one thing here, when we have a maximum or we have a minimum, that's where we actually change from having a positive first derivative to having a negative first derivative. So when we have that sign change, we have a horizontal tangent line, and that's when our derivative is actually equal to 0. And that's what we found up here when we found our critical numbers by setting each factor equal to 0 to get these two numbers that divide up our sign chart. Okay, so just to kind of look at this here, if we're talking about the interval from A to B, so any open interval, if the derivative is greater than 0, so if it's positive, then the function's increasing. If it's negative, it's decreasing. So basically, like I just said, if you have a positive first derivative, that means the graph is increasing, or in other words, it's rising when you go from left to right. And there's different ways that a graph can rise. It could rise as just a plain straight line. It could rise with what we call an upward concavity, or it could rise in a way that it's concave down. And we'll talk about that more in section 4.2. Same thing if you have a negative first derivative, that means your function's decreasing or falling from left to right. And it can fall in various ways as well. It can fall concave down, it can fall concave up, or it can be just a straight line. So looking at this, you can see that it is still falling as it goes from left to right. and so it would have a negative first derivative over that interval. Okay, so our first example that we're really going to do some work for is this function here, and we're asked to find the values of x that correspond to horizontal tangent lines. So going back for just a minute to our previous example here, we said that at these places where the derivative is equal to 0 is where we have a horizontal tangent line. So that's what we need to find on this one, is the places where our derivative is equal to 0. So our derivative then, we take the derivative of this, it's going to be 8 minus the derivative of x squared is just 2x. And if we set that equal to 0, okay, we want to solve this and it's just linear, so it's going to be 8 is equal to 2x. Divide away the 2, and so we get x is equal to 4. So that is going to be the value of x that corresponds to a horizontal tangent line, because a horizontal tangent line has a slope of 0. And remember, your derivative is equal to your slope at a given point. So when x is 4, that is when we have our horizontal tangent lines. Okay, so for which values of x is f of x increasing or decreasing? This is where we want to create our sign chart. Okay, so our sign chart, we're going to put that critical number that we just found, which we found the 4. Okay, so what I want you to do is I want you to think about, we're going to plug into the first derivative and we're going to see what that tells us about the actual function itself. Okay, so our first derivative, I'm going to put that back up here so we can look at it, is 8 minus 2x. Okay, so if I plug, let's say something greater than 4, let's say we plug 5 in to the derivative, that's going to be 8 minus 2 times 5. So that's going to be a negative. Okay, so it's negative over here. If I put in maybe 1, because 1 would be in this interval, then that's going to be 8 minus 2 times 1. So that's going to be a positive. Okay. So what that tells me is if my first derivative is positive, that means the actual function is increasing. If my first derivative is negative, which it is on this interval, then that means my regular function is decreasing. Okay, so to answer our question, our function is increasing from negative infinity to 4. Okay, so from negative infinity, which is back here, to 4. And then it's going to be decreasing when it goes from 4 to infinity. Okay, so what that actually means, and we'll talk more about this later, is if we're increasing up to a point and then we decrease again, then that means we actually have a maximum that's occurring here. And you can see a graph here of the actual function we were looking at. And here at 4 is where we get this change from the function increasing to decreasing, and we have the horizontal tangent line at that maximum value. Okay, here's an example that would be a good one for you to try. Okay, for this one, to find the horizontal tangent lines, we need to set the derivative equal to 0. So my derivative for this one is going to be equal to 2x minus 6. So 2x is going to be equal to 6. Divide both sides by 2. So x is going to be 3. So that is going to be the location of my horizontal tangent line. As far as which values is it increasing or decreasing, that value of 3, which we call our critical number, is what is going to split up this sign chart. And so we're going to have our first derivative and what it's going to do to our original function. So our first derivative was equal to 2x minus 6. So if I pick a number greater than 3, let's say 4, okay, 2 times 4 is 8 minus 6. That's going to give us a positive. And then if I pick something less than 3, like maybe 1, 2 times 1 minus 6, that's going to be a negative. So that means my original function, because the derivative is negative, is actually going to be decreasing this time. And then over here, since it's positive, first derivative is going to be increasing. So our function decreases and then increases. Okay. So as far as always finish up the problem by literally interpreting this graph. So it increases from 3 to infinity and it decreases from negative infinity to 3. Okay, so we've talked a little bit about critical numbers, but here's our definition. A real number x in the domain of f, so it does need to be in the domain for it to be a critical number. So it's in the domain of f such that the derivative is equal to 0 or the derivative does not exist. So we've seen examples where the derivative equals 0. We have not seen examples where it does not exist, but both can provide us with critical numbers to put on our sign chart. Okay, your textbook calls them partition numbers. Basically, these are just the numbers that divide your sign chart up. Okay, all right, so if we take a look at this one, we're asked to find the critical numbers of f, where it's increasing and where it's decreasing. So if we look at this, we know that to find our critical numbers, we need to work with the derivative. I mean, pretty much every problem you're going to work with the derivative in some respect. So here the derivative of 1 is 0. Here the derivative is 3x squared. So we want to set that equal to 0. We'll divide both sides by 3. So x squared is 0. You take the square root of both sides. The square root of 0 is in fact 0. Okay. So that means we're going to put 0 on our number line and see what happens. Okay. So when we do this, if we put the number 1 into our number line, into our first derivative, then our first derivative was back over here, 3x squared. So if I put 1 into that, then that's going to be positive, okay, because a 1 squared is still positive. If I put negative 1 in, 3 times negative 1 squared, a negative 1 squared becomes a positive, so this is a positive. So what happens is, because my first derivative is positive for both parts, it's actually increasing for both intervals. So we would say that it is increasing for all x. Okay. We don't have what's called relative extrema, because in order to have relative extrema, which would be a relative maximum or a relative minimum, we would actually have to have a sign change here, and we don't have a sign change. So this is increasing. It kind of flattens off and has a horizontal tangent, but then it increases again. So it looks something like that. Okay, so let's look at this one for practice. Go ahead and try this one. All right, let's take a look at this one. This one's a little bit different than what we've been dealing with, because all the others that we've dealt with were polynomials and fairly simple. This one is not a polynomial, so we need to consider things about considering like the domain and where our first derivative is not defined for this one. So looking at this, like I've said before, we know we're going to start out by taking the derivative. So the derivative of this is going to be 1/3 times 1 minus x. Take away 1, so this will be the negative 2/3. And then the derivative of this inside function would be negative 1. So I'm going to have negative 1 over 3 times 1 minus x to the 2/3. Okay, so that's my first derivative. It's certainly messier than what we've dealt with before. But if you remember, your critical numbers are either where the derivative is equal to 0, or they're where the derivative is undefined. Okay, so looking at this, you get the places that this is equal to 0 by looking at the numerator. So there's no place that negative 1 is equal to 0. But there is a place, we get the undefined from the denominator. There is a place that would, a value that would make the denominator be 0. So I want you to think about here. If I put x equals 1 into this, then I'm going to have 1 minus 1 is 0. So I have 0 in the denominator, which makes that undefined. Okay, so f prime of 1 is undefined. So that means that that's one of our critical numbers that we're going to put on our sign chart, and that's going to break our number line up into increasing and decreasing intervals. So from here, once we figured out what our critical numbers are, we're still going to go ahead and do everything the same as we did before. So if I pick a number more than 1, let's say 2, and plug it into this derivative, I'm going to have negative 1 over 3 times 1 minus 2 to the 2/3. And if you're not sure about that and you want to just put it in your calculator, you're going to see that that actually is going to turn out to be a negative number. If you plug 0 in, because 0 would be from this interval here, you're also going to see that you end up with a negative number. Okay, so we end up with 2 intervals that are decreasing. Okay, so we've got decreasing and then decreasing again. So we're going to say it's decreasing for all x. So one last comment here. We don't have a sign change of our first derivative, so that means that we don't have a relative extrema here, because we don't change from being like increasing to decreasing or decreasing to increasing. We just stay decreasing the whole time. One thing we didn't really talk about is the domain on this. Because you're taking an odd root, because this will be the same thing as the cube root of 1 minus x, we can take odd roots of negative numbers, so we don't have to put any restrictions on the domain for this. This is a look at the graph itself, so you can see that it is decreasing to 1. We have a vertical tangent line, which is why that first derivative is undefined, and then we continue to decrease. So we actually switch what's called the concavity of it, but so this goes from being concave down to concave up, but it's still decreasing. Okay, this is a very similar one to what we just did. If we look at the first derivative here, that's going to be 1/3 times 1 plus x to the negative 2/3. The inside derivative of this one would just be 1. Okay, so we're going to have 1 over 3 times 1 plus x to the positive 2/3. So here we don't have any place that this is equal to 0, because 1 does not equal 0, but the denominator does give us a place where it's undefined. So if I'm looking for where this is undefined, 1 plus x is equal to 0 when x is negative 1. So on my sign chart this time, the place that the first derivative is undefined is at negative 1. So I need to analyze on either side of negative 1. So let's say I put 0 in. 0 is a number more than negative 1. If I put 0 into this derivative here, I'm going to have a positive first derivative. Let's say I put in a negative number, like maybe negative 2. That's going to be 1 over 3 times 1 plus negative 2. So that's also going to be a positive. So what that means for our original function is this would be increasing and then increasing. So we don't have a sign change, so we don't have a maximum or minimum. So we would say that it's increasing for all x, because the domain of this original function here, we don't have any restrictions on it. So we could say it's increasing for all values of x. Okay, this one actually provides some interesting, an interesting look here. If we look at the derivative on this one, I would first do a rewrite of it and write it as x minus 2 to the negative 1, because otherwise you're going to have to do the quotient rule. So when I take the derivative, which you should be comfortable doing by now, we're going to bring that down in front. recopy that inside function, decrease the power by 1, and then follow that by the derivative of this inside, which would just be 1. So I'm going to have negative 1 over x minus 2 squared. Okay, so looking at this, I want to see where is that first derivative equal to 0, and is there any place that it's undefined? Okay, so the place the first derivative would be equal to 0 is if that numerator would equal 0, but negative 1 won't equal 0, so I don't get anything there. But I do have a place where this first derivative is undefined. So my first derivative is undefined when x equals 2, because that's what would make that denominator be 0. So when x equals 2, the function's undefined. So that's the number that I want to use on my number line here. Okay, so looking at this, if I put, let's say, 3 into this function, okay, I'm going to have a negative 1 over 1 squared, so I'm going to end up with a negative. Let's say I put 0 in, I'm going to have negative 1 over negative 2 squared, so I'm also going to end up with a negative. So I'm going to have a decreasing function and another decreasing function. So the tendency would be to say it decreases for all values of x, but there is actually one value of x that's not in the domain of our original function. And so if we look back at this, we can see that when x equals 2, that is actually not in the domain. So since it's not in the domain, we can't actually say it decreases there. We have to say on this one that it decreases from negative infinity to 2, and then again from 2 to infinity. But we do need to exclude the value of 2. Okay, and you can kind of see what the graph looks like here. So we've got, it does decrease here, and then it also does decrease here, but there is a break in it, so it's not continuous at x equals 2. Okay, here's a good one to practice with. I would first rewrite this as x to the negative 1. So my derivative then is going to be negative 1x to the negative 2, or negative 1 over x squared. Okay, if we think about the domain of this function, the value that x cannot be is 0. Okay, but it's also, x equals 0 is also the value that makes that first derivative undefined. So that is going to be one of our critical numbers. Okay, so when I go to plug into this, when I put something more than 0 in, I'm going to get a negative. If I put something less than 0 in, like negative 2, I'm going to have negative 1 over negative 2 squared. So that is also going to be a negative. Okay, so I've got it decreasing and decreasing, but we can't include that 0 because our domain excluded 0. So it decreases from negative infinity to 0, and then also from 0. Okay, if we look at this one, same instructions here. If we take the derivative, that's going to be 5. The derivative of natural log of x is 1 over x, and then this would be minus 1. So we want to look at, so we've got 5 over x minus 1 is equal to 0. Okay, I'm going to move the 1 to the other side, and then I'm going to cross multiply. So when I cross multiply, I'm going to multiply x times 1, and then the 5 times 1. Okay, so x equals 5 is going to be our critical number. We do also need to keep in mind that when we look back at our original function here, we see that the natural log is not defined for negative numbers, so our domain is simply x has to be greater than 0. So we're actually not going to be able to go past 0 here, okay, because x has to be greater than 0. And if we look back at this first derivative, we see that x cannot be 0 because of it being in the denominator here. and it would make that first derivative undefined if x were 0. So we cannot include 0 as part of our answer, but 5 will be one of our critical numbers. So we're going to look at plugging into this first derivative. So if I put like 6 into the first derivative, that would be 5 over 6 minus 1. Well, 5/6 minus 1 is going to be negative. If I put maybe 4 in, that would be 5/4 minus 1. That's going to be positive. Okay, so our function, we're plugging into the first derivative, but it's telling us something about the original function. So our function here is increasing and then decreasing. Okay, so it increases from 0 to 5, and then it decreases from 5 to infinity. And remember, our function's not defined for negative numbers, so we can't go below 0. It's the reason we have this instead of infinity. Okay, so we've talked a little bit about local extrema. So when we have a continuous graph and it's rising and falling, you can have high points or local maximums. And then sometimes when it goes from falling to rising, you have low points, which are your local minimums. So looking at this, if we look, we can see that we have a low point or a local minimum that we have would be here at C2, C sub 2, and again at C sub 4. Because at both of these places it goes from, say, decreasing to increasing, decreasing to increasing. We could have local maximums. So local maximums go from increasing to decreasing. So C sub 3 would be a local maximum. We'd also have a local maximum over here at C sub 6 because it would be increasing to decreasing. When we look at these other values, like, so not those that are not a local extrema would be C sub 1 because we don't change. We go from decreasing to decreasing. And also here at C sub 5, we go from increasing to still increasing more. And then again at C sub 7, because we don't change, we go decreasing, decreasing. Okay, so as far as like interpreting it in terms of our derivative, because this is a decreasing function, if we were talking about the first derivative, it would actually be a negative first derivative. This one would be a negative first derivative. Now here we're rising, so it would be a positive first derivative. Falling again, so negative. Rising would be positive first derivative, positive, negative, and negative. So you only get these local maximums and minimums when you see that sign changing. So when it goes from negative to positive, it's a local minimum. When it goes from positive to negative, it's a local maximum. And these are just formal definitions. F of C is called a local maximum if there's an interval that contains C such that f of x is less than or equal to f of C for all x in that interval. Just saying that it's the highest point, basically. And if it's the lowest local minimum, then it's the lowest point, again, in that interval, not for the entire graph, but just in an interval near it. And then local extrema includes both local maximums and local minimums. Okay, so we want to use the graph of G in the figure to find the intervals on which G is increasing and where it's decreasing in any local maximums and local minimums. So here we're just working with a regular function and we're just listing where it's increasing and where it's decreasing. Okay, so looking at this, we can see that here it's falling. Okay, so we're gonna, it's falling from, so it's decreasing from negative infinity. This would be -3, to -3. And then it turns and it increases. We always write these in terms of the domain, so it increases from -3 to 1. And then it turns around and decreases the rest of the way. So it's going to decrease from 1 to infinity. So what that means is because we went from a negative first derivative to a positive to a negative again, it means this here at x equals -3 would be a local minimum, and at x equals 1, it's going to be a local maximum. Because we have a peak, it's going from positive. Okay, so we have a theorem here. If f of c is a local extremum of the function f, then c is a critical number of f. So basically, when you're looking for your critical numbers, you're looking for your local extrema. So the theorem says that local extremum can occur only at a critical number, but that does not imply that every critical number would produce a local extrema. So it's possible to have a critical number, and we've seen this, where we don't have a sign change, and therefore it's not a local extrema. So essentially you have to have a sign change. So if the first derivative exists on both sides of a critical number, and the sign of the first derivative can be used to determine whether the point is a local maximum, minimum, or neither. And that's the first derivative test that tells you if you have a local minimum or a local maximum. So we can have different things that occur. Your first derivative can go from negative to positive, and in that case, you're working with a local minimum. Okay, so here if you go from positive to negative, you go from increasing to decreasing. So on this, you're going to have a local maximum that's occurring there. Okay, on this one, you don't have a sign change, so you're looking at something going increasing and then increasing again. So when you have no sign change and they're both increasing, then you have neither a local maximum nor a local minimum. And then the fourth case, if they're both negative, it's decreasing and then decreasing again. So again, no sign change means no local maximum or local minimum. Okay, so in a function f of x, when the derivative is equal to 0 for some value x equals c, then there's a horizontal tangent at x equals c. And again, we've seen that the horizontal tangents occur when we potentially when we have the first derivative equal to 0. So in these examples here, when you have a local minimum, you have a horizontal tangent line because you have that sign change there. Here you've got the sign change, but so it's going from positive to negative, so that means there's somewhere in there that equals 0, and that's going to be where that horizontal tangent is. Okay, if you have no sign change for a function f of x when the derivative is equal to 0 from value for some value of c, then there is a horizontal tangent. So you can have this horizontal tangent even when you have no sign change. It just means you don't have a maximum or a minimum occurring, but you can have a horizontal tangent line. Okay, so even if you've got a situation like this where the derivative is not defined. So the ones we were looking at previously here, we had smooth curves and the derivative was actually equal to 0, so you had a horizontal tangent line at those places. But if you look at something like these here, you do still have a local minimum and a local maximum, but because you've got this sharp point here, your derivative is actually not defined. So anytime you have a sharp point on a graph, you're not going to have a derivative that's defined. So so just kind of watch for that. So you can still have local minimums and local maximums even when the derivative is not defined, so long as you have the sign change there. This one is just another example of when you have a derivative that's not defined. So one place you have undefined derivatives is when you have sharp points in the sharp turns in the graph, but the other time is when you have vertical tangent lines. So here, because our tangent line would actually be vertical for this one, the derivative is undefined. So in this case, the f of c is neither a local maximum or a local minimum because we don't have the sign change and it's not defined. Same thing here, we're going with two negatives, so there's a vertical tangent line. and that's why the derivative is not defined. So this is kind of putting it all together. We want to look at these examples and find our critical numbers. So I'm going to start by taking the derivative here. So we're going to have 3x squared minus 12x plus 9, and we want to set that equal to 0. This is a polynomial, so we don't have to worry about places that's undefined or anything like that. Okay, to simplify this, what I'm going to do is I'm going to take 3 out as a GCF. So x squared minus 4x plus 3. Okay, so when I factor this, I'm going to have x, this would be minus 3, and x minus 1, because we want things that multiply to give us 3 and add to give us 4. So that would be 3 and 1. Okay, so we're going to set these factors equal to 0 to get our critical numbers. So in this case, we actually have 2 critical numbers. Okay, so I'm going to put these on the number line here, and I'll be sure that you put them in order, okay? So we've got 3 and 1, so 1's going to come first and then 3. And we want to look at analyzing this first derivative. Okay, so we're going to pick our test point. So if I pick a point between 1 and 3, let's pick 2. I always go back and plug it in here, like in the factored form. If I'm plugging 2 in, 3 obviously is positive. If I put 2 in here, that's negative. So I've got positive, negative, and then this is going to be, if I put 2 in there, it's going to be positive. So if I'm multiplying a positive times a negative times a positive, I'm going to end up with a negative for that middle section there. If I put the number 4 in as a test point, that's going to give me positives for everything. So this section is going to be positive. And let's say I put 0 in for the test point for this region, then I'm going to have a positive, a negative, and another negative. So 2 negatives multiplied together is going to give me a positive. So for my original function, it tells me, since it's a positive first derivative, it tells me it's an increasing function. Negative first derivative tells me it's decreasing. And then another positive first derivative tells me that it's increasing. So my critical numbers, be sure that you actually answer the question. Sometimes you can get kind of caught up in what you're doing. Your critical numbers are 3 and 1. If we want to find the next question, which is the local maximums and minimums, if we look back at what we have here, you can see that we go from a positive to a negative first derivative, which means we go from increasing to decreasing. So I have a local maximum that's occurring at x equals 1. And then here I go from a negative to a positive, so it's going decreasing and then increasing. So I have a local minimum that occurs at x equals 3. Okay, and if you're asked to find the point, the actual coordinates of the point, then what you're going to do is plug back into the original function. So I'm going to put 1 back here. And when I plug 1 in, f of 1, that's going to be 1 to the third minus 6 times 1 squared plus 9 times 1 plus 1 is going to give me 5. So my local maximum occurs at 1, 5. And then do the same thing here. So 3, and then plug f of 3, plug 3 into f. So f of 3, you can check this, f of 3 is 1. So my local minimum occurs at the point 3, 1. Here's a graph of it just to kind of give you a look at what's happening. You've got the increasing part up to this local maximum, which we said is at the point 1, 5. And then here we've got the point 3, 1. That's our local minimum. Okay, here's one for you to practice. Okay, our derivative for this one is 3x squared minus 18x plus 24. So we do have a GCF, which is 3. And I would go ahead and factor this into two parentheses. So we need, actually this should be an 8. We need numbers that multiply to give me 8 and add to give me 6. So that's going to be 4 and 2. So if I set each of those equal to 0, I'm going to get 4 and 2. So that's my critical numbers. All right, as far as determining if they're local maximums or minimums, you do have to show this number chart. Again, make sure you put them in the right order. So 2 comes before 4, not 3. So, okay, so 2 and 4. We're going to plug into the first derivative, and it's going to tell us about the original function. So my first derivative that I'm going to plug into is going to be here. Okay, so the factored form of that first derivative. So if I put, let's say 5 as my test point here, then that's going to be positive, this will be positive, and this will be positive, so that's a positive region. If I put maybe 3 in, that's going to be a positive, 3 here would be a negative, and then 3 here would be a positive, so I'm going to have a negative, positive, negative, positive gives me a negative, and then over here maybe 0, that's going to be a positive, here would be a negative, here would be a negative, so 2 negatives give me a positive. So I've got the function is going to be increasing, then decreasing, and then increasing again. So that means here at 2, since it's increasing and then decreasing, we're going to have a local maximum at 2. And then here we're decreasing and then increasing, so we're going to have a local minimum at 4. Okay, so our local max is going to be 2, and then I'm going to plug 2 into the original function to get the coordinates of the point. And so that looks like, you can double check this, but if I plug 2 in here, it's going to give me 10. And then my local minimum is going to be 4. And I'm going to plug 4 into, again, the original function, and that's going to give me 6. So when you're doing your test points, you plug those into that first derivative. But when you're finding the coordinates of your local maximums and minimums, you plug those critical numbers into the original. And this is just a look at the graph. So we've got increasing up to that point, 210 that we said was a maximum, local maximum. And then over here, it's going to be a local minimum at 4, 6. Okay. So even though this is a place where it changes from increasing to decreasing, it's not what we call an absolute maximum, but it is the highest point in that region there. And this is like not the absolute minimum, but it's the lowest point in that region. Okay, so theorem 3, talking about intercepts and polynomial functions. So if we have a polynomial and it has degree that's, your degree is n, so if it has a degree of at least 1 or more, then it has at most n x-intercepts and at most n minus 1 local extrema. So basically if the degree is 4, what it's saying is that it could have at most 4 x-intercepts, and it could have at most 3 maximums and minimums, so 1 less than your degree. Okay, there's no guarantee that it has that, but it could have as many as that. Okay, so a couple economic applications here. Let's orient ourselves to this graph. So this is the graph of the derivative, not the original function. And this is talking about the rate of change, which is our derivative, of the price of eggs over a 70-month period. E of t is the price of a dozen eggs, and t is the time in months. Okay, so we want to determine when the price of eggs was rising or falling and sketch a possible graph. So as far as the rising and falling part, what we need to think about is what we've been given and what we're asked to provide information about. So we've been given, in this case, the derivative, and we need to provide information about the original function. So I would say go back to our sign chart and think about the way that we set this up. We always put the derivative on the top and we put our original function on the bottom. Okay, so what we want to look at is we always want to know we want to figure out where is the derivative positive and where is it negative. Okay, so what happens is that derivative graph, because this is our derivative graph, is changing from being negative to being positive here at 10. So 10 would be one of our critical numbers, and because we also have a sign change here, 50 is going to be another one of our critical numbers. So our derivative, because it's below the x-axis, is negative, and then it's positive for this whole part here, and then it goes back negative again. So we have a negative first derivative, then a positive, and then another negative. So that means the original function was decreasing for the first 10 months, then it was increasing from 10 to 50, and then it decreased again. Okay, so as far as the price, because the price of eggs is the E of T, then the price of eggs was rising from the 10th through the 50th month, and then it was falling from 0 to 10 months, and then again from 50 to 70 months. Okay, so to summarize it here, like just what we said, the price of eggs is falling before month 10 and after month 50. And it's rising between months 10 and month 50. This is actually what the graph looks like. I'm not really that concerned that you can generate the graph as long as you can interpret that graph that we started with. All right, here's one for you to practice, very similar to what we just got through doing. Okay, so this one you are you are given the derivative. So kind of the same idea. Set it up with your sign chart and look and see where is it that your first derivative is changing signs. Okay, so this one, it looks like that's at 1, 2, 3, 4, 5, 6. So we've got a sign change at 6 because it goes from negative to positive. Then we have another sign change at 16 because it goes from positive to negative. So we have negative, positive, negative. So it's decreasing, increasing, and then decreasing. And it's not unusual for different quantities to decrease at first before you start making a profit and things of that nature. So, so you can see that we actually have a minimum here at 6 and we have a maximum at 16. The S of T is the U.S. share as a percentage of the total world production of motor vehicles over a 20-year period. So basically, the U.S. share peaked at about the 16th year in this 20-year period. Okay, so just the U.S. share of the world market decreased for the first 6 years, which we said that, and then to a minimum, increases for the next 10 years to a maximum, and then decreases for the final 4 years. And that's kind of what we were saying. Okay, this was a graph of revenue. So obviously you want to maximize your revenue when you're looking at this. So write a brief description of the graph of the marginal revenue function, including a discussion of any x-intercepts. Okay, so this is our derivative, our original function, and we want to describe the graph of the marginal revenue. So that would be describe a graph of the derivative function. Okay, so I'm going to kind of go back to what we know with our sign charts. Okay, except this time, since this is r of x, we need to think about what can we see here. Okay, so since this is our original function, if I'm looking at this original function, I see that it's increasing up to about 450. Okay, so it's increasing over that interval, and then it decreases. Okay, that's from 0 to decreases to 1,000. Okay, so looking at that, we can see that we have a maximum here that occurs. So if I'm going to translate all this into the first derivative, that means that if my original function's increasing, I have a positive first derivative, and then I have a negative first derivative from 450 to 1,000. So looking at this, what are R of X is the revenue from the sale of desk. So basically, we have a positive change in our revenue for the first 45 desks that we sell, and then we have a negative change in our revenue for the last from 450 to 1,000.